Hey class, and welcome back to chapter 11, the last chapter of the semester, unfortunately. Anyway, in this chapter we're going to be discussing fluids and everything associated with it. And again, just so you know, a fluid is any liquid or a gas, right? So anything that can take the shape of its container. I really enjoy talking about the physics of fluids. It's fascinating. It includes one of my favorite forces, which is the buoyancy force. And so I'm going to break this chapter into kind of three sections because there's a lot of topics that we're going to be covering. In this first section, we're going to primarily talk about static fluids, so fluids that are stationary or not moving and the physics associated with those. And then we'll move on in later parts of the chapter to talk about fluids that are actually in motion, making some simplifying assumptions initially and then adding more complexity as we build on. So here we go. First of all, to understand when we're dealing with fluids, where again, keep in mind fluids applies to both gases and liquids. Those are both considered fluids. When we're talking about fluids, we're often going to be dealing with the density of fluids rather than just the mass, because sometimes knowing the exact mass of a quantity of fluid can be tricky, especially when talking about gases. So just to remind you, you've probably learned this already, but density, we use the Greek letter rho. It looks an awful lot like a P, but it is a rho. Notice it's slightly different. The Greek letter rho is density, and it's equal to mass divided by volume. In this class, we'll be using the SI units of kilograms divided by cubic meters, although you've probably seen a series of different things such as grams per cubic centimeter, grams per milliliter in chemistry class and other places. So here's a series of different densities, common densities of solids, liquids, and gases, just to give you an idea of some of the different densities you'll come across and see. And a lot of times you can look up different densities online. I do encourage you, if you're doing any homework problems, especially using Wiley Plus, make sure that you use the densities listed in the textbook, because otherwise you might get a slightly higher percent error being off by rounding and other things, which might have the online homework report you as wrong. So be careful with that. So now I want to have us do a practice problem. So let's imagine that we have a man who has a total weight of about 690 newtons. All right, and within this man's arteries and veins, he has blood that takes up a volume of about 5.2 times 10 to the negative third cubic meters. Based on that information alone and the density of blood given, I want you to tell me what is the total weight of blood in this man's body and what is it as a total percentage of his overall body weight. And maybe before you get started, I'd encourage you, just estimate. What do you think? What percentage of the average human body by weight is composed of blood? What would you guess? 5, 10, 20, 50% of your overall body weight is blood? What do you think? So give it a go and then we'll do it together. You can pause, but I'm going to keep going. So first of all, to figure out the weight of blood, we know weight is mass times gravity. So we first need to figure out the mass of blood. And so since density is mass over volume, you can see mass is just going to be volume multiplied by density. So if we take the volume of the blood, we multiply by the density of the blood, we see in all he has about 5.5 kilograms worth of blood in his body, which is actually quite a lot, right? There's 2.2 pounds per kilogram. So actually I got my calculator here. So we're looking at, I can't type, hold on. All right, we're looking at about 12 pounds of blood, quite a bit, no messing around. So we do that in terms of newtons. Weight is mass times gravity, do the math, and we have a box-worthy 54 newtons worth of blood in this man's body. And then we find it as a percentage of his overall weight, 54 newtons, divided by his 690 newtons worth of total weight, and we're at about 7.8% of his overall weight is blood. Crazy, right? All right, so next thing I want to talk about, again, we're redefining some of the things we typically deal with, because with fluids, we're not always going to just be concerned about mass and force. It gets a little tricky dealing with those types of things. Instead, we're going to be dealing with pressure and density. So pressure, just so you're aware, we kind of briefly mentioned it earlier, but pressure is when you have force being dispersed over a given area. So pressure is just equal to force divided by area. 1 Pascal is equal to 1 Newton divided by 1 square meter. And so the reason we're going to deal with pressure, if you think about air pressure inside of a tire, right? Hopefully you put air in your tires at different times. That pressure is going to be pushing in all directions. As you put more and more air in there, those air molecules are going to be bouncing around, hitting all surfaces, and those air molecules bouncing around generate a force, and that force is what gives rise to the pressure. And so as you can see on here, you're going to have force on the inside edge of the tire, you're going to have force on the rim, you're going to have force on the outside edges of the tire as well. It's going to be on all different parts. And so instead of trying to figure out the force, because force is pushing around everywhere, instead we're going to talk about pressure, which will give us how much force is on each square meter of surface area. All right, and so again, this is Pascal. So 1 Pascal is the SI unit for pressure, as we discovered back in chapter 12, and it's equal to 1 Newton divided by 1 square meter. So normally I do a fun demonstration here. Since we're online, I can't do the live demo for you. But what I do, I'll just go ahead and tell you. I take a aluminum can like this one here. I put just a little bit of water in it. I boil that water until it's starting to boil and evaporating, okay? And then I'll take the can and I'll turn it upside down. There's still a little left in here, so I'm not going to do it. But I turn it upside down in a bunch of hot water, or sorry, cold water. What's in here has become hot and boiled. There's only a little bit, keep in mind. I turn it over in cold water, and guess what happens to the can? Boom, it crushes almost instantly, all right? Why? What crushes the can? Again, I heat up the little bit of water in there till it's evaporating, it's boiling. Turn it upside down and put it in cold water. What crushes the can and why? Think about it. It's an interesting idea. Guess what? The thing that crushes the can when I do this demonstration is actually the air in the room. Atmospheric pressure is what's able to crush the can. What happens is I heat up the little bit of water in here until it evaporates, and so what I end up with is high temperature water vapor inside my can. So it's hot water vapor. What pressure is it at? Well, since the can's open, it's just at atmospheric pressure. Things always want to be at the same pressure whenever possible, so you have equal pressure inside the can and outside. I then turn it upside down in the cool water. That high temperature water vapor cools down. What happens when things cool down? They condense. They take up less space. And what happens to the pressure? According to the ideal gas law, the pressure inside my can decreases. And so now the pressure inside the can is much lower than atmospheric pressure. And so the pressure on the inside wants to become even with the pressure on the outside wants to become even with the pressure on the inside. And so the pressure of the air, the pressure in this room, just pushing down on my shoulders, my desk, my computer, the pressure in this room is what's able to crush the can, which is quite amazing. And so again, that is atmospheric pressure. Where does atmospheric pressure come from? What gives rise to it, do you think? Well, from the atmosphere and from gravity. Gravity is pulling down on all the air molecules in the atmosphere. There's a bunch of air molecules right here, right? Gravity is pulling down on those, all right? There's some air molecules here too. They're being pulled down by gravity. And so you really sitting on top of your shoulders when you're standing really inside or outside, but it's easier to visualize outside. When you're standing outside, you have literally miles of air just sitting above you being pulled down by gravity, and all that air has weight, and that weight is pushing down on you and on the surface of the earth and on everything around it, and that's what gives rise to atmospheric pressure. Now another question is, atmospheric pressure, pretty cool, pretty interesting. Is it the same everywhere in the atmosphere? What do you think? Well, the answer is no, as you might know. So, yeah, I grew up in Reno, Nevada. I went to graduate school in Colorado. Both places were approximately 1 mile above sea level, so an elevation of around 5,000 plus feet. 5,000 feet further away from the center of the Earth means 5,000 feet less of Earth's gravitational pull and 5,000 feet less of air stacked above me. And so at those elevations, there's actually less atmospheric pressure. And so what we find is that while we say atmospheric pressure is a different value, usually what we're going to use is 1.013 times 10 to the 5th pascals, or 101.3 kilopascals. You can also express it in other units like psi, torr, and millimeters mercury. But what we find is atmospheric pressure is actually a gradient, okay? Which means the pressure changes as you change in elevation. So the pressure right here is actually a little bit higher than right here. Pressure right here is actually a little higher than right here. You don't notice a huge difference in these tiny little changes in pressure, but you really notice it when you go up into the mountains or other places. Something I remember when I was growing up, and especially this seemed to happen, I don't know why, a lot to me when I was in Colorado. I think for some reason I used to eat yogurt a lot when I was teaching at a community college in Colorado. One time when I was in the middle of teaching, I'd taken my yogurt, I opened it, and that yogurt had been prepared and packaged down at sea level. It had been sealed, and so the little bit of air inside of there was atmospheric pressure, about 101 kilopascals. I was up at elevation at a lower pressure, and so that high pressure air inside there, the moment I opened it, it wanted to go flying out. Well, it brought with it a bunch of little yogurt particles, and I had a bunch of yogurt particles stuck to my shirt, this little like haphazard pattern of sprayed white dots all over my shirt the rest of the day. Ever since, I always now open yogurt away from me. So don't stand in front of me if I'm opening yogurt because it might spray you. Although now I live closer to sea level, so it doesn't happen, but it's a habit that I formed, and I always open yogurts away from me because of pressure. Under pressure. Anyway, okay, so this is all cool, and we see it in the atmosphere, but guess what? You probably have also noticed that it occurs in water as well, and the change with elevation or depth in water is much more dramatic. I remember as a kid, I would dive down, to the bottom of a swimming pool that's like 10 or 12 feet deep, and man, my ears would just start hurting like crazy. I'd feel this intense pressure pushing on my eardrums, or at least that's what it felt like, and it just was really uncomfortable because as I go down in the water, there's more water above me pushing down, and so there's an increase in pressure. So what I want to do now is I want to use the physics that we've learned to derive what is that change in pressure as you go down in depth. How do you quantify that difference with depth in water? So let's look at, here's a chunk of water right here. We're going to take this chunk of water and do some of the forces analysis on it. All right, so let's think about this. There's the top surface of this chunk of water, there's a bottom surface to it, and then itself has some mass and gravity. So if we do some of the forces, there's a force at the bottom due to pressure at the bottom, which we'll call P2. There's a force at the top due to the pressure at the top, which we'll call P1, and then there's the weight of the water itself. Keeping in mind, pressure is force over area, so pressure times area is force. So we do some of the forces. We got pressure 2, which is at the bottom, times area 2, which gives us the upward force at the bottom. Then we have P1 times A1 at the top, but it's going down, so it's negative. And we have the weight of that chunk of water, which is also down because it's a gravitational force, right? And so this is what the sum of the forces looks like. Why did I set it equal to 0? Well, this is just a chunk of water floating in the tank. It's not moving up and down. There's no acceleration, so net force is 0. Cool. So we got P2 times A equals P1 times A plus mg. That's a nice equation, but what's pressure? What's this area? We just made up this random chunk of fluid. What does that even mean, right? So let's make a couple substitutions. As I mentioned earlier, when we're dealing with fluids, we like to deal with volume and density and pressure instead of mass. So mass is volume times density. So let's make that substitution real quick. Okay. Then what else? Well, volume, again, this is some arbitrary chunk of water that I made up, right? So let's do a substitution. Volume is just going to be the area of the top multiplied by the height, however far you've changed vertically in the water. So let's plug that in. And now look what we see. Oh, boy howdy. Area, area, area. Boom, we can cross those all out. And what we find is the amount that the pressure changes from the top of the water to some depth below is just dependent on how far down you've moved in the water and the density of the fluid. So if it's water, we know its density. If it's salt water, it's slightly different. If you're in a pool of, I don't know, make up some random honey or something like that, then it'd be even a different change in pressure. But the change in pressure is just based on the density of the fluid and how far you move vertically through that fluid. So, conceptual question based on this idea, right? I grew up in Reno, Nevada, not that close to Lake Mead, but Lake Mead and the Hoover Dam are on the border of Nevada and Arizona. And so you see here, there's this massive lake, Lake Mead, this artificial actually reservoir that's a result of the Hoover Dam. All right, so let's imagine that, for some strange reason, Hoover Dam started losing water. Lake Mead started losing water. This big reservoir started dropping, but they wanted to keep it looking the same near the reservoir. So at the very back, they started filling in with dirt. As you lose water, you keep filling in with dirt, keep filling in with dirt, keep filling in with dirt, until you just have a column of water right here. So instead of the lake being like 100 miles across the top, you have just like, 3 meters across the surface of the water, but the same depth as before. Maybe some of you are aspiring civil engineers. What could you do to change the structure of the dam, knowing that now you don't have so much water behind it, you just have the same depth of water, but only 3 meters across the top? What could change? Do you come up with a guess? Maybe pause it, think about it, talk to a friend or somebody. The answer is nothing. This dam would have to be the exact same thickness at all points. Why? Because pressure is only a result of the depth of the water. It doesn't matter how much water is back there when it comes to pressure. Down here at the bottom, the pressure will be the exact same pushing on the dam as if you had the whole lake, if you're still at the same exact depth. Okay, so depth doesn't matter how much water there is, only how deep into the water you are. What would matter is if the dam were to break, the amount of damage that happens downstream. A lot more water brings a lot more energy. All right, so let's just do a quick calculation practicing this idea. Here's two different points, point A here and point B over here under this chunk of land. Okay, you can't really tell, but let's imagine that, directly above point A, here you're half of this distance. All right, so 2.5 meters below this overhang of dirt here, but still 5.5 meters below the surface is point B. What is the pressure at point A and what is the pressure at point B? Pause it and give it a go. So hopefully you tried it out. Again, pressure at some depth is equal to the pressure at the top plus rho GH. So pressure at the depth is what we want for point A. The depth, the H, is 5.5 meters. P1, what is that? A lot of people just say, oh, it's 0, right? You're at the top. No, that's atmospheric pressure. The air is still pushing down on top of that water. So you have atmospheric pressure up here, okay? Then you have which is 1.013 times 10 to the 5th pascals. You have the density of water, G and H, plug and chug, boom. The pressure at this depth would be 1.55 times 10 to the 5th power pascals. So about 1.5 times what it is up at the surface of the water. What about point B over here? Exact same. You're at the same depth below the surface. All this dirt and stuff doesn't matter. It's just about the pressure built up in the water. As long as it's connected in the same body of water, then the pressure up here at all points is atmospheric. As you go down, you're gaining this much extra pressure as you move down in depth. Another cool example, I don't know if you've ever noticed, but there's these units for pressure, millimeters mercury, right? Where does that come from? Well, it comes from old barometers. What is a barometer? Well, it's a device used to measure barometric pressure, or pressure in the atmosphere. So the way they're originally designed is there's this tube, okay, this glass tube. Up at the top of the tube, you pump basically all of the air out of there. So you have a vacuum up here, which means the pressure up here is 0, okay? Then, as atmosphere, the air in the room pushes down on the mercury here, it's going to force the mercury to move up this tube. How far is it going to move it up the tube? Well, this equation tells us, right? Because what happens is we have a situation where P on top, P1 is 0, P2 then is the pressure down here pushing the water up, or excuse me, the mercury up. You can use water and other things actually as well, but it's going to push this fluid up here, and so now you're going to have pressure down here at the surface must be the same at the same elevation. So the atmospheric pressure pushing down on the fluid here is the same as the pressure inside the tube at point A, and so therefore the pressure, atmospheric pressure here, must just be equal to rho GH, where H is the depth of the fluid. What's rho? Well, rho is going to be the density of mercury. So here's the density of mercury, there's atmospheric pressure, and there's gravity. And so 1 atmosphere of pressure will push mercury up this thing almost a meter, 3/4 of a meter, 760 millimeters. So 1 atmosphere of pressure equals 760 millimeters of mercury. That's the density of mercury, in case you didn't know. Cool. So again, how does this work with pressure gauges? Let's imagine this is like your tire or something. You put pressure in your tire. How do you determine what the pressure is inside your tire? Well, one way would be to use mercury and see how high the mercury moves, right? So you have atmospheric pressure on one side, you have a higher pressure on the inside, and the height difference here is going to tell you about the pressure difference between atmospheric and inside of here. And that difference between those two pressures, P2 minus atmospheric, is something known as the gauge pressure, okay? So if you ever see or hear or learn about gauge pressure, like when you're measuring the pressure of your tires, that gives you the gauge pressure. That's not the absolute pressure, but rather the difference between the pressure inside and the pressure out where you are. Now, if you know atmospheric pressure, you can just subtract to figure out the absolute or real pressure, but gauge pressure is the difference between the two. All right, so the next thing I want to introduce is Pascal's principle. All right, so what Pascal's principle tells us, it's really quite impactful, very useful and practical, especially in engineering. It says that any change in pressure applied to an enclosed fluid is evenly transferred at all places. What does this mean? Well, let's say that I pump more air into my tire, right? So really, if this is my tire and I have one little, connection for my hose here, and I'm pushing air in just at this location, well, as I increase the pressure there, that increase in pressure is going to be spread everywhere throughout the fluid. So it means pressure is spread at all places throughout a given fluid. The cool thing about this is that it's very applicable to pneumatics. Things like a pneumatic jack and so on enables you to really take advantage of Pascal's principle to gain mechanical advantage. And so, for example, with this car lift, with a relatively small force, you can lift a very heavy object, which is pretty neat. And in fact, I'm going to have you do a practice problem with that here in just a second. So, how does this work? What equations govern Pascal's principle? Well, if we have these two locations, if they're at equal height, for example, when you start, then the pressure at them must be the same, right? So at that point, since pressure is force over area, that means force over area here is going to be equal to the force over the area here. And so you can relate the different forces. They're just going to be related to one another in correspondence to the relative areas. So F2, the amount of upward force you can generate on the car, is just going to be equal to whatever force you supply multiplied by this ratio of areas, A2 over A1. So let's do an example with this. All right, so here's this car lift you're going to use. You're going to apply force F1, all right, onto cross-sectional area A1. You're given the radius of the input piston here, and that's going to generate a force that's trying to lift the car over here at A2, which is given by this. You have this radius of that piston there. And what you're told is that the car and the plunger that it sits on together have a total weight of 20,500 newtons. All right? My question to you all is, assuming that they're even, so we're not looking at this setup here, but assuming that they're even, okay? Assuming that they're even, what is the force required to just get this start to move? So assume that there's no acceleration, but how much force is required to make this move or keep it moving at a constant velocity? So pause the video, give it a go, and let's see what you get. So here's what I did. Pascal's principle tells us that F2 is equal to F1 multiplied by the ratio of these areas, but we want F1, not F2. So F1 equals F2 times the inverse of that same ratio, A1 over A2. And from there, it's just plug and chug. We're given F2, 20,500 newtons, area 1, area 2, pi r squared for both of those, and you should get about 131 newtons. So to lift this 20,500 Newton car and piston would only take, ideally ignoring friction and other things, would only take a box-worthy 131 newtons of force. Quite crazy, right? So anyway, that wraps up kind of the introduction to chapter 14. We covered a lot so far. I think I'm going to stop here, call it good for this video, and then we'll come back in the next video to talk about my favorite force, the buoyancy force.